Some weird and wonderful observations fitting the Poisson distribution. Poisson himself thought of his discovery as a little curiosity, a little eddy by way, and apparently did not really use it very much. The first person who put Poisson's observation to good use was von Botkiewicz, who in 1898 published an intriguingly titled book, Das Gesetz der kleinen Zahlen, which translates into The Law of Small Numbers. This is a curious book. You'll find in it analyses of suicide rates in children, among women, fatalities, death. Maybe there was a morbid streak in his makeup. But one absurdly remarkable application that he focused on, and that has received a lot of attention since, is of fatalities in the large Prussian army of the late 19th century, where people died as a consequence of being kicked by their horses. Let's take a look at what von Botkiewicz actually looked at. So he followed 14 army corps for a period of 20 years, from 1875 to 1894. Now, each army corps has got a large contingent of troops in it, and if you followed them for 20 years, you have 14 times 20, or 280 army corps years. In each year, you have one particular army corps in that year. You have a lot of individuals in that corps, and there are many horses. There are many opportunities for being kicked and dying. Okay, so here, success means getting kicked and dying. It's a little morbid, a little macabre. But if this is the case, then within each corps year, you have something like a binomial distribution. A large number of individuals, a small chance P, hopefully, of getting kicked by a horse and dying. And he finds that in that period, about 280 army corps years, there were 196 fatalities, which translates into lambda equal to 196 over 280, or about 0.7 fatalities per army corps year. So approximately one person in each army corps in a given year died. All right, now what are the data and support of this? Well, here we go. So you have a table in front of you where on the left you have the number of deaths per corps year. The deaths, column K, are 0, 1, 2, 3, 4, 5, and so on. Here are the observed frequencies. 144 army corps years had no deaths. That corps in that year had no one dying. 91 army corps years exhibited one death. 32 exhibited 2 deaths, and so on. Again, if you think of these as a setting where you have rare events, the chance of getting kicked by a horse and dying is small. Army corps have got large numbers of individuals in them. We've got something, a binomial distribution governing it. And this is approximated by a Poisson distribution. And what is the parameter of the distribution? Well, it's your lambda. Lambda is 0.7. If, in fact, the deaths were governed by these probabilities, with these frequencies, these Poisson probabilities, then the expected number of army corps years with no deaths would be 280, the total number of corps years, times the corresponding Poisson probability. And that is listed on the third column. And one thing that will immediately strike you is how remarkably good the fit is. Of course, this does open up questions about how one tests for goodness of fit, but we will come to that a bit later. For our purposes now, this shows us a beautiful fit of the Poisson approximation to the data.